Chapter 3, the derivative. In this chapter, we are going to move into the first major branch of calculus called differential calculus. We're going to focus on looking at rates of change and looking at a bunch of applications in engineering and science and in business, of course. Let's start out with section 3.1 and introduce the derivative. So in this chapter, we're going to learn about a function called the derivative. Derivatives describe rates of change. All right, so the first kind of example of a rate of change that we'll look at is velocity, right? Velocity is the rate of change of position over time. There are a couple different kinds of velocity. In this next example, we're going to sort of observe the differences between average velocity and instantaneous velocity. So here's a very simple example. To get to work each morning, Jeremy drives about 11.5 miles over the course of 15 minutes. Suppose the graph below shows Jeremy's distance from home t minutes after leaving home. So we're not given any specific function here. We are just given this graph. Now, to make sure that we understand this graph and how it works, I just want to look at a couple of ordered pairs on the graph. So here's an ordered pair. This is the ordered pair 5, 3 is what it looks like. So what does 5 represent? What does 3 represent? Well, remember this horizontal axis represents time, so this is like our t-axis. And the vertical axis represents distance from home in miles. So this ordered pair 5, 3 tells us that after 5 minutes, I am 3 minutes away from home. All right, we can also look at this ordered pair. So this one tells us that after 10 minutes, I must be 9 miles from home. And this last ordered pair up here, just looking at the real obvious ones and focusing on these intervals of 5 minutes, after 15 minutes, this is when I am 11.5 miles from home. And this is when I presumably arrive at work. All right, so let's answer some of these questions. First, is Jeremy traveling the same speed during the entire trip? Explain. So we're just looking at the graph and trying to determine, answer this question about the speed at which I'm traveling. So what do we think? Are we going the same speed this whole time? You might be thinking no, just kind of intuitively. I mean, this is not a velocity graph, right? This is a distance versus time graph, but this is a question about speed. But why would you think that we're not going the same speed throughout this whole trip? Well, sort of intuitively, just looking at this graph, there are parts of the graph where the line is steeper, and then there are parts of the graph where the line is not so steep. So that kind of seems like we might be going faster where it's steeper and slower where it is, has a smaller slope. Why would this be? Well, if we just look at this first interval from 0 to 5, how far do we go during those 5 minutes? Well, we go from 0 miles from home to 3 miles from home, right? How about in the second 5 minutes? So from 5 to 10 minutes after leaving home. We go from being 3 miles from home to 9 miles from home, right? So see how we cover a larger distance. Here we only cover 3 miles. Here we cover 6 miles. Okay, so that implies that we're going different speeds at various points during the trip. So I might say here, no. I'll say less distance was traveled on the time interval, and I'm just going to use interval notation here, on 0 to 5. Right, like we just said, over that interval of time, I traveled 3 miles. Compared to that second interval from 5 to 10 minutes, here I traveled 6 miles. Okay, but the really, really important observation here is the slope of the line of this distance versus time graph indicates the speed, the rate of change, or the velocity. Okay, so for part B, we want to actually calculate what is the speed that I'm traveling during the first 5 minutes. Okay, so speed, what is speed? How do we calculate it? Well, speed, this is kind of like velocity. There's a slight difference. We'll discuss that a little later. But basically, speed is the change in distance over the change in time. So the change in distance over the change in time. Okay, so that triangle that I just drew, in case you haven't seen that, that is called, this is a Greek letter. This is a Greek letter delta. And in math and in science, and you know, you'll see this in physics and engineering, it means change in. Okay, so we'll be using that quite a bit throughout this entire course, really, from now on. Okay, so change in distance over change in time. And the unit might be worth noting that distance, the units of this is going to be miles. And what are the units of time? Remember, this is all based on this graph that we're given up here. The units of time are minutes. Okay, so how do we calculate or compute the change in distance and the change in time? Well, okay, we're looking at the first 5 minutes. So let me zoom in on the graph here. We have this ordered pair 5, 3 we were talking about. Also, there's the starting point. I should have labeled this. This is 0, 0, right? 0 minutes after leaving home, and at that point, we are 0 miles away from home. So the change in distance, looking at the graph, that's just going to be the change in the, you know, the output values of the function. Or it might kind of look like the change in y, since we normally associate the vertical axis with the y variable. So the change in distance is just going to be the final position minus the initial position. So in that case, it's going to be 3 minus 0. Okay, so that just came from the, you know, the y coordinates. All right, and then how about the change in time? That's just going to be the difference in the t coordinates. So that'll be 5 minus 0. And remember, that is measured in minutes. All right, so this simplifies to 3 miles over 5 minutes. And since this represents a rate of change, you might say this 3 miles per 5 minutes, right? That fraction sign, that division sign, represents the per in the rate of change. Now, this is a really weird way to describe a rate of change, particularly, you know, if we're talking about speed or velocity. We don't measure velocity or speed in terms of miles per 5 minutes. I think the most common way, at least around these parts, would be miles per hour. So this could be our answer. You know, that is like a valid rate of change, but I would much rather represent this in miles per hour. So I'm going to convert this, and to do that, I'm going to use what we call a conversion factor. Okay, so off to the side here, bear with me for a second. We want to convert from minutes to hours, right? I don't like this miles per 5 minutes thing. I want it to be miles per hour. So remember that 1 hour is equal to 60 minutes, right? So I'm going to multiply by a conversion factor, which is going to be a fraction involving these two values. And what I'm going to do is I'm going to multiply by 60 minutes over 1 hour. And why am I allowed to do this? Why am I allowed to just, introduce this factor here? Well, since 60 minutes and 1 hour are the same value, right? They're the same amount of time. This is just a big 1. So I know it doesn't look like it since the numerical values in the numerator and denominator are not the same, but 60 minutes is equal to 1 hour. Therefore, 60 minutes over 1 hour is just equal to 1. Okay, so that's why I can get away with doing this. So here's what happens. The minutes cancel out. Okay, so we sort of think of the units as being factors in this multiplication problem here. And, I could have put hours on top and minutes in the bottom, but I did it this way because I wanted the minutes to cancel out. So those cancel out, and I'm left with, 3 times 60. And we still have the miles units up top. And down in the bottom, we have 5 times, 1 hour. So we have the hour units down here. And you can simplify this fraction, 3 times 60 divided by 5. The number we end up with here is 36 miles over 1 hour, or I could just write that as miles per hour. Okay, so quite a few things happened in that part B there. We were trying to calculate the speed. That involved calculating the change in distance over the change in time. We ended up with 3 miles per 5 minutes, and then we multiplied by this conversion factor to get it into miles per hour because we were asked specifically to do that. And we got 36 miles per hour. Okay, so that was our rate of change, or that was our speed over this interval right here. So something I want to point out here is to calculate the speed over this interval. What I did is I did the change in distance over the change in time. Notice that really the formula that I use there is the difference of the y's over the difference of the x's. Do you remember this formula? y2 minus y1 over x2 minus x1. That happens to be the slope formula. Okay, slope as in slope of a line. So we actually just calculated the slope of this line. So this totally validates that sort of intuition that we had earlier in this problem, thinking about, oh, are we going the same speed throughout this whole entire 15-minute period? And I was thinking, oh, well, I see different slopes of lines. It's like we're covering greater distances over the same amount of time in certain intervals. And kind of intuitively, it's like, oh yeah, it seems like that means we're going faster. This totally confirms that. Okay, this confirms that the slope of the graph of, that displays distance versus time, the slope is going to be the same as the speed over that interval. Okay, so slope, rate of change, it turns out they're kind of the same thing. Let's keep going here. Let's look at this second interval now from 5 to 10 minutes. So we can go through this more quickly. It's going to be the same process that we just went through. So the speed over the second interval, again, it's going to be the change in distance over the change in time. All right, and to calculate this, since we're looking at the second interval now, we can use these two ordered pairs. All right, so 5, 3 and 10, 9. Okay, so we'll take the difference of the distance value. So final distance was 9 miles from home minus the initial distance, which was 3. Okay, and that will be in miles. And in the denominator, it's going to be the difference of the t coordinates, which is going to be 10 minus 5. And this is in minutes. So for this one, I get 6 miles per 5 minutes. Again, kind of a weird way to describe the rate of change, given that we're talking about a speed. I'd much rather say it in miles per hour. So let's multiply by that conversion factor, 60 minutes over 1 hour. That will cause the minutes to cancel out and we'll be left with hours. So that's good. And we can multiply straight across like we did in the last one. This time we're going to get 72 miles per 1 hour. All right, so we expected to be going faster during this second interval from 5 to 10 minutes, and the math confirms that. It looks like we're actually going twice as fast, which makes sense because over the second interval of 5 minutes, we traveled twice as far as we did during the first 5 minutes. Okay, and then the last interval for part D from 10 to 15 minutes. The speed will be change in distance over change in time. I'm just going to jump straight to it. Here, the two ordered pairs we'll use will be the last two. So I'll do in the numerator 11.5 minus 9. That's the change in distance, and the change in time will be 15 minus 10 minutes. So that gives me 2.5 miles per 5 minutes. Okay, and then multiplying by the conversion factor, I'll let you show the work for that. We get 30 miles per hour. Okay, so it seems like, in this car ride to get to work, maybe in this first 5 minutes, this is like, driving through town, trying to get to the freeway. And then the second 5 minutes, 5 to 10 minutes into the trip, this is like we're on the freeway going 72 miles per hour. And then we get off the freeway and we're coming down Hesperian or something. All right, going 30 miles per hour until we get to work. Okay, so I think we have a pretty good grasp on what's happening in this example here as described by the graph. Part E, the last question is it possible to figure out Jeremy's average speed over the entire trip? If possible, calculate the average speed. Okay, so, when I'm teaching this class in person, oftentimes people are like, oh, we could take those 3 speeds that we just found and add them together and divide it by 3. And it turns out that you actually can do that in this case. You can do that in this example. That's not always going to work, but it does work here because these happen to be just, lines, straight lines. Like these are little linear functions in each of these intervals, and these intervals are all the same size. Okay, they're all 5-minute intervals. Okay, so it turns out that you can just take the average of those 3 numbers, add them together and divide it by 3. However, that is not the easiest way to do it necessarily, and it's not going to work in every situation. Okay, sometimes if we have different sized intervals, which we will in examples, we're not going to be able to get away with it being that simple. But the good news is that it isn't too hard to find the average rate of change over the entire trip. We just need to calculate one more slope, and it happens to be the slope of the line that just goes from the first ordered pair, 0, 0, to the last ordered pair at 15, 11.5. So really, we are finding the slope of this line. So that purple line right there is what we're going to do next. Okay, so is it possible to find the average rate of change? Yes. We just need the first and last ordered pair. Okay, so the average speed, and by the way, those ordered pairs are 0, 0, that first one, and the last one was 1511.5. So we're going to use those 2 points. So the average speed is going to be the overall change in distance over change in time. And let's calculate that. So that'll be the difference of the y coordinates. So 11.5 minus 0, that'll be in miles. Whoops, miles. And then over 15 minus 0 minutes. So we just get 11.5 miles per 15 minutes. I'll multiply by that conversion factor of 60 minutes over 1 hour just to get it in terms of miles per hour. And if you simplify this, you're going to get the minutes to cancel out. We'll have an answer in terms of miles per hour, and it simplifies down to 46 miles per hour. So does this number make sense? Like, does this seem right? Yeah, I think it does, because in the first little bit we're going 36 miles per hour, second little bit we're going 72 miles per hour, and then 30 miles per hour. So I imagine it'd be some number, between 30 and 72. We got 46 miles per hour. That sounds about right to me. Okay, so we can just use those first and last points to find the average speed. So let's do another example, kind of continuing exploring this idea of average velocity, and then we're going to work our way towards finding the instantaneous velocity. Okay. So one thing just to define clearly, average velocity can be calculated by finding the change in position. So change in position over the change in time, or the average rate of change of the position function. Okay, and a position function is just where the horizontal axis is time and the vertical axis is going to be some measurement of distance, like miles, or in this example it's going to be meters. Okay, and then it represents the slope of this thing we call secant lines. Okay, and a secant line is just when you draw a straight line through any two distinct points on a graph. Okay, so this purple line that we drew in the last example, that purple line is an example of a secant line. All right, so secant lines will allow us to find average rates of change. Okay, so here's the example. If a rock is thrown upward on the planet Mars with velocity in terms of meters per second, its height in meters, t seconds later, is given by this function s of t, which is equal to negative 1.86 t squared plus 10t. Okay, so s is commonly used to represent position. Okay, So s, don't confuse that. Don't think that's speed or something like that. S is generally used to represent position. So looking at this graph, we have the t-axis, and then we have the s of t-axis. And we could just note that this is in terms of meters. This is going to be in terms of seconds. All right, so again, let's kind of do that thing where we look at the graph, look at some ordered pairs, and try to decide, you know, what the ordered pair means, interpret the t and s coordinates. So like if I look at this ordered pair right here, right, I'm just picking this one because this is, oh, sorry, not that one. I want to pick this one. This is where t is equal to 1. Okay, so the first coordinate is going to be 1. And the second coordinate, the s coordinate, we can compute by just plugging into the function here. Right, so this is going to be s of 1. Off to the side, I'll just calculate. Okay, what is s of 1? Well, this is going to be negative 1.86 times 1 squared plus 10 times 1. All right, and for this, what we get is 8.14. You can have your calculator out for this, for sure. So the ordered pair is 1, 8.14. So let's interpret this. What does this ordered pair mean? Well, the 1, this is a measurement of time. So that's going to be 1 second. And that coordinate there, the 8.14, this is measured in terms of meters, right? So really that's 8.14 meters. So what this point tells us is, okay, remember this rock is being thrown upwards on the planet Mars. After 1 second, the rock is 8.14 meters in the air. Okay, so this is like the height. This is the height of this space rock. So a common misconception looking at a graph like this is it's easy to assume that this represents horizontal distance and this represents vertical distance, and we're looking at some kind of trajectory, you know, like the rock is thrown and it follows this path. But that actually is not what we're talking about here. Here we're only measuring height. So really we're not thinking about the horizontal distance that is covered by this rock at all. For our purposes, we could just think of this rock as being thrown directly upwards, right? Reaching some maximum height and then coming directly back down. Okay, so I just wanted to clarify that this horizontal change right here, that is a change in time. It's not like it's moving from left to right or something like that. Okay, so just want to make sure that we're clear on that. One more ordered pair I'm going to look at for right now is when t equals 3. So when t equals 3, you can plug into the function. You know, what is s of 3? Plug 3 in for t here. You can do that on your calculator. I did that and I got 13.26. Okay, so I just want to come up with those 2 points because what are we asked to do in part A? We want to find the average velocity between t equals 1 and t equals 3. So this is saying, you know, on that interval from 1 second after this rock is thrown upwards to 3 seconds after the rock is thrown upwards, what's the average velocity over that time interval? So like we just were kind of discovering in that last example, I can calculate this by just finding the slope of the secant line. So let me just draw in this line here. If I just calculate the slope of that secant line, that line that goes through those 2 points at t equals 1 and t equals 3, that will give me the average velocity. Okay, so let's do it. So we want to find average velocity. Sometimes I'll denote this v with a little subscript AVE, so that just stands for velocity average. it's going to be the change in distance, or in this case, I guess the change in height over the change in time. So I can get that by taking those two s coordinates. So it's like s of 3 minus s of 1. And in the denominator, we'll just have 3 minus 1. And remember our units, up top this time it's in meters, and down in the bottom it's in seconds. Okay, so plugging in the actual numbers that we got, it's going to be 13.26 minus 8.14, and in the denominator, just 3 minus 1. Simplifying this down, I end up with just 2.56. And the numerator was meters, the denominator was seconds. And this time I don't have to do a conversion factor, because remember up here we kind of indicated we're looking at the velocity in terms of meters per second. So we didn't do anything, we weren't given these values like, if we were asked for meters per hour or something like that, we would have had to do a conversion. But since the t-axis is measured in terms of seconds and the s-axis is measured in terms of meters, they're being a little nicer here. We don't have to do a conversion. We just get meters per second right away. So there we go. The average velocity, and again, we're just thinking in the vertical direction, like how quickly is it moving upwards or downwards, over this interval from 1 to 3 seconds is 2.56 meters per second. Okay, let's do part B. We want to find the average velocity from t equals 1 to 1.5. So how about I go over here to 1.5, that is this ordered pair right here, and let's figure out what the output value is. If I put 1.5 into this function, what I get out, again, used my calculator for this, 10.815. 10.815. All right, and I just wanted to get that ahead of time because now I want to compute the average velocity between t equals 1 and 1.5. So that's going to be s of 1.5 minus s of 1 over 1.5 minus 1. And this is going to be meters up top. It's going to be seconds. That's the units in the bottom. Whoops, seconds. And plugging in those values from the function, it'll be 10.815 minus 8.14. In the denominator, I'm just getting 0.5. All right, and then running these numbers through my calculator, it all simplifies down to just writing in decimal form again, 5.33 meters per second. Okay, so what this is telling us is that the velocity, just in the upwards direction, was greater over this interval from t equals 1. Let me just mark this out on the t-axis. So here's t equals 1, there's 1.5, and then here was 3 over here. The average velocity was greater between 1 and 1.5 than it was over this interval from 1 to 3. Okay, so same starting point, but different average velocities. Okay, or we could draw the graph of the secant line through these 2 points, through t equals 1 and 1.5. I'll do it in a different color. How about in blue? And we see we get a steeper line here. Okay, so everything is, all these concepts kind of work together. We see a steeper line. That means it has a greater slope. That means the average velocity should be greater, because remember, average velocity or average rate of change and the slope of the secant line are the same thing. All right, and then thinking of the application, it's like we threw this rock upwards, right? And then it slows down due to gravity and then comes back down. So since we're looking at a smaller interval nearer in time to when we initially threw the ball, we have a higher velocity because it hasn't slowed down so much due to gravity. Okay, so we have a lot of kind of overlapping, intersecting, equivalent concepts at play here. But that's why these first two examples here are so important, because these are concepts that are going to follow us throughout this calculus course, and kind of playing around with these examples and seeing how they all interact is really helpful. But we're all just getting used to it, so yeah, you'll have an opportunity to practice this on homework and all that. You can ask me questions, of course, in office hours or over Canvas. Okay, so we calculated a couple different average velocities. So what we are kind of headed towards is, okay, we can find average velocity over some interval, right? How do I find instantaneous velocity? Instantaneous velocity, we could think of this as like what your speedometer on your car is telling you at a given moment, or like if highway patrol hits you with a radar gun and it gives off some speed that you're supposedly going at that very moment. That is instantaneous velocity. And instantaneous kind of indicates that it's at a single moment in time. Okay, so here's the obstacle. To find all of these rates of change, or these velocities here, we needed two ordered pairs. We needed 2 points in order to do it. And instantaneous velocity is asking what is the speed at just 1 point. How can we find the slope of a line through just 1 point? Well, remember the slope formula. This thing, if we're just trying to find the slope of a line, this formula requires that there are two ordered pairs, right? It requires an ordered pair x1, y1, and it requires an ordered pair x2, y2. And finding velocity so far, we've needed to use this formula. So we've needed 2 points. So how can we possibly find instantaneous velocity if there's only one ordered pair? This is like the first major problem that differential calculus was, developed to try to address. Okay, so this next, I'm just trying to sort of set up the motivation for why we're going to do this weird thing in part C, where we say, find the average velocity from t equals 1 to t equals 1 plus h, where h is some positive real number. So let's just sort of run the math real quick. So if we want the average velocity over this weird kind of abstract time interval here, if we're looking at the graph, again, let's say that there's 1, and how about right here, just at some random spot, let's say that this is t equals 1 plus h. Okay, and I'm drawing this to the right of t equals 1 because we're assuming that h is positive. Okay, so it's going to be some movement in the positive direction. So if this is 1 and this is 1 plus h, this distance between them, right, just the width of this time interval is h. The width of the time interval is h. Okay, so like if we're looking at this first example, the width of this time interval from t equals 1 to t equals 3, this is where h was equal to 2. Right? Because from 1 up to 3, the width of that time interval is just 2, right? So there's 1, and then there was 1 plus h, which gave us 3. Okay, or for part B, like what was h in this case if we were looking from t equals 1 to t equals 1.5? how much time has passed from t equals 1 to t equals 1.5? Well, h in this case is just going to be 0.5. Okay, so when I say the width of the time interval, that's kind of a, like visually looking at the graph, we see a width. But in terms of, just time that has passed, that's really what that represents. The width of the time interval is how much time has passed from the initial time to the final time. So for part C, we're just sort of generalizing it. We're just saying, abstractly, like for any time interval from t equals 1, starting at t equals 1 and, going a distance of h, we want to find that average velocity. So let's do it. We would plug into the function. We would get s of 1 plus h, right? Because we do the final position first, minus s of 1 divided by 1 plus h. That's the final time minus the initial time, which is just 1. All right, numerator is in meters. Denominator is in seconds. So this will just simplify down to s of 1 plus h minus s of 1 over h. Right, because the 1 minus 1 in the denominator just simplifies down to this. So this is like our formula here. And one nice thing about this formula is that h, notice that before the denominator was like the change in time. So h just represents the change in time. So h is equal to change in time. This can kind of help simplify and streamline the process for computing a lot of average velocities, which is what we're going to do in a second. Okay, so on the next page, let's move on here. This is the same example. We're still talking about this rock being thrown on Mars. A little definition here. So instantaneous velocity could be thought of as I was saying earlier, the speed you see on the speedometer in your car at any single moment. And it represents the slope of the tangent line, or the limit of the slope of the secant lines. Okay, let's talk about what a tangent line is. I'm going to go back to the graph for a moment here. So a tangent line, I'm just going to draw it in here. Take these away, make a little room for it. A tangent line is a line that goes through a single point on a graph and perfectly mimics the slope of the graph at that single point. Okay, so let me draw it in here. So right there, so here's a line, and what makes it a tangent line is that it only intersects the graph at that one point. All right, so in order to achieve this, we need this line to perfectly mimic the slope of the graph. Because think if you took this line, let me pull out my ruler. If this line was tilted at all, like there, all of a sudden, if I drew that line, it's actually intersecting more than one point of the graph, right? Or if I tilt it more, right? If I tilt it like that even, right? See, if I draw that line, it's going to intersect the graph at 2 points, right here and right here. Okay, so in order to achieve this really kind of unique situation, I redraw my tangent line here. We need the line that we draw to have the exact same slope that the graph does at this particular point, in this case at t equals 1. So this is what we call a tangent line. All right, so a secant line intersects the graph at 1 point, or excuse me, at 2 points. A tangent line intersects the graph at 1 point. So finding the slope of a tangent line is really tricky because of that problem. We only have one ordered pair. We're used to having two ordered pairs to find the slope of a line. So that's the big problem that we have to overcome. So check it out. Here's how we're going to overcome that issue. If we look at a bunch of different intervals here, so I have a little table set up here. We're looking at a bunch of different intervals. So we already looked at these first two. That's what we did in part A and B. This was like where h was equal to 2, right? The width of the interval was 2. Here, the width of the interval was 0.5. The next interval we're going to look at is the interval that has a width of 0.1. Next, we have 0.01. You might be thinking, whoa, this is looking a lot like when we used to compute limits, right? And we'd be picking values of x that were closer and closer to x equals 1 or something like that if we're looking at a limit at 1. And yeah, you are absolutely right. This is exactly what we do to compute a limit. That is how we find the instantaneous velocity. So we will see what happens to the average velocity as h gets closer and closer to 0. So in other words, we are trying to approximate the limit as h goes to 0 of that formula that we just found a second ago, s of 1 plus h minus s of 1 over h. Okay, so it turns out that instantaneous velocity, or v inst, as I sometimes write it, we can calculate it using this limit. So this is the workaround, right? There's that issue. How do we find the slope of a line? Not based on two ordered pairs, but really based on the function and a single point, a single t value in this case. The way we do it is we take the limit of the slopes of the secant lines. Okay, so back to the picture, and I'm sorry for all the jumping around. This is a very, very kind of conceptually dense first section of this chapter. Just kind of working our way towards what we'll see is actually the derivative. The idea is we're going to calculate the slopes of all of these secant lines, right? We started with this one, and then we did this one, and then we'll do this one, and then we'll do this one, right? Just getting closer and closer and closer to that tangent line without actually getting to it. In other words, taking the limit as this interval h shrinks to get smaller and smaller and smaller and smaller. Okay, so let's actually do that work now. So we already did the first two of these, right? We found that over the time interval 1 to 3, the average velocity was 2.56 meters per second. Over h equals 0.5, we got 5.33 meters per second. And now, okay, let's compute it over h equals 0.1, so that would be s of 1.1 minus s of 1 over 0.1, right? Because if h is equal to 0.1, we're just calculating the average velocity over this interval here from 1 to 1.1, so that would look like this. And I'll let you do the work on your calculator, plugging in 1.1 into the function, taking the difference, doing the division. I got 6.097 meters per second. Okay, and then next, let's look at s of 1.01 minus s of 1 over 0.01. Again, using that formula, this one up here. That's where we're just dividing by h. Okay, and here, I plugged these in just so we can kind of check together. I got, for s of 1.01, I got 8.2026, right? And then minus 8.14, and then divide that by 0.01. So that's what I got using my calculator, and then simplifying, I got 6.26 meters per second. Okay. And this last one, I did all that same stuff, but with h equals 0.001. And I got approximately 6.3 meters per second. So what it looks like we're getting closer to, right? Remember we would do this exercise in chapter 2 where it's like, all right, as we plug in values that are closer and closer to t equals 1, it looks like the output values or the average velocity functions are approaching, we could just say 6.3 meters per second. So what I can say here is that the instantaneous velocity, which as we saw is equal to the limit as h goes to 0 of s of 1 plus h minus s of 1 over h. It looks like this is going to be, I'll just say approximately, right? We're just kind of approximating here, 6.3 meters per second. Okay, so looking back to our graph, what we found is at t equals 1, at t equals 1, at this point right here, this Mars rock, which was thrown upwards, is traveling instantaneous, has an instantaneous velocity of about 6.3 meters per second. Equivalently, the slope of that tangent line, so I could say m tan, the slope of the tangent line, that's something we'll write, is approximately 6.3. Okay, so thank you for bearing with me through this example. I know there's a lot of stuff going on, but the big topics, the big things that I want you to take away from this example is average velocity graphically, and relative to a position function, is calculated by finding the average rate of change, which is the change in position over the change in time. And average velocity is over an interval, meaning we can have two ordered pairs which allow us to find a slope of a secant line. Okay, so average velocity is kind of the easier one to find. Instantaneous velocity is way trickier. This is, in order to find this, we need to find the slope of the tangent line, which ends up being the limit of the slope of all the secant lines. Okay, so we have to go through this process of computing a limit. All right, and sometimes we'll have to do this table of values thing, but we are going to very soon find that there are actually some techniques for computing instantaneous velocity or an instantaneous rate of change, and that, the thing that allows us to do that really quickly and efficiently and easily is called the derivative. Okay, so take a deep breath. Try to let that soak in a little bit. And we move on a little bit closer to the actual definition of the derivative. Okay, let's talk about the difference quotient. Okay, we're getting really, really close here. So just hang on. So the difference quotient, we'll start by finding the slope of a secant line. Okay, so we're talking about some function f, that's like this kind of greenish line here is the function f. Like we were just discussing, we have secant lines, that's going to be just a straight line through any 2 points on the graph. So to find the slope of a secant line, and we're just sort of labeling on the x-axis, let's say this first point is just x, and the second point is just x plus h, so really laying this out in the same way that we were previously, but we're not talking about a function that's modeling anything specific, like change in height of a moon rock over time, or a Mars rock, sorry. But still, h is going to represent the width of this little sub-interval here of the real number line. So the slope of that secant line is going to be the difference of the y's over the difference of the x's. So just looking at these ordered pairs, this ordered pair is x plus h, and then the output, the y coordinate, is just f of x plus h. Okay, that's that ordered pair, and this one down here is just x f of x, right? Just your normal function graph. The input is the x coordinate, the output is the y coordinate. So the slope of the secant line will just be the difference of the y's, so that will be f of x plus h minus f of x over the difference of the x's, which is going to be x plus h minus x. And this simplifies to just f of x plus h minus f of x over h, right? Because the positive x and negative x in the denominator cancel out. So this is just a generalized form of that formula that we found in the last example in part C, right? Like we kind of already found this formula, but we're just generalizing it for any function f and for any x value x. So this is what we call the difference quotient. So what we'll do is we will be looking at specific functions and trying to compute the difference quotient for that given function. And here's what it's going to look like. What it involves is taking this formula for the difference quotient that we just found and then substituting in a function. So the thing that's tricky about this is I think we're used to plugging values into functions, you know, like if f of x equals x squared, it's like, oh, what's f of 2? Well, that's just going to be 2 squared, which gives us 4, right? Like we're used to doing this, plugging numbers into functions. But in this process here, what we're actually going to be doing is, it's like the thing we're substituting in is actually the function itself, right? So we have this formula here, and in for f, I want to substitute this function x squared. So how do I do that? Well, f of x plus h. What is f of x plus h if f is x squared? Well, that's just going to be x plus h squared. Like here, I'll kind of highlight this. Right, x squared is our function, so that's what happens if we plug in x plus h into the function. And here, this is what happens if we plug x into the function. Right, so f of x, that's just the original function there. And then once you do that, you want to simplify. Here the work is kind of shown. Remember, x plus h squared, we have to FOIL that out, so we get x squared plus 2xh plus h squared. And then simplifying a little bit, notice that we have positive x squared and negative x squared, so those will cancel out, and then we're just left with 2xh. And then we factored out an h, right? Because between these two terms that were left over, we had a common factor of h, so that got pulled out. Those two cancel, or they make a big 1, and we're just left with 2x plus h. So that is our simplified difference quotient for the function x squared. All right, so again, a little weird, a little tricky. You know, we're substituting in a function into this formula rather than a real number like we have many times before. But this is how it works. Let's do one for real now. Our function this time is f of x equals x over x plus 1. So a little rational function here. And we want to compute the difference quotient, so we're going to be substituting into this f of x plus h minus f of x over h. So, okay, what is f of x plus h going to look like in this case, given that this is our function? So the way that it works, whenever we substitute something into a function, wherever we see the variable, in this case x, we want to plug in this input x plus h. So that's what we're going to do. So the first term in the numerator is going to look like this. It's my function, except wherever there was originally an x, I'm going to put x plus h. So I'll have x plus h in the numerator, and then in the denominator, I used to have x plus 1. This time I'm going to have x plus h plus 1. All right, and then the second term in the numerator is just going to be f of x, so our original function, x over x plus 1. And in the denominator, we'll just have that h. Okay, so the trickiest term to come up with is just this f of x plus h. But everything else is pretty straightforward. It's just the function itself over here and then h in the denominator. So we always want to try to simplify this. And best case scenario is we get this cancellation with the h. Okay, we'll see in just a little while why it's important that we get that cancellation. But let's just try and simplify this. What should we do? Well, I have fractions inside of fractions, which is generally not a very good thing. I could get out of that predicament by perhaps adding these two fractions together in the numerator. So how would I add these two together? Well, I'd have to get common denominators. So to get common denominators, I could multiply this second fraction by x plus h plus 1 on top and bottom. And then I'd multiply the first fraction by x plus 1 over x plus 1. Right? Taking this route because there are no common factors between these two denominators here, so kind of have to go this route. All right, let's see what happens. The first fraction, multiplying the numerators together and the denominators together. So in the numerator, we'll get x plus 1 times x plus h, and in the denominator, we'll get x plus 1 times x plus h plus 1. Okay, I'm getting rid of these parentheses up here just because addition is associative. Okay, and then subtracting from that, this other fraction will be x times x plus h plus 1 over x plus 1 times x plus h plus 1. Okay, just multiplying straight across, still whole thing is over h. So I have common denominators now. I might multiply this out, like I could distribute this x into those terms, and then I could FOIL out those two factors down there. And here's what I would get. So over here, I'll get x squared plus xh plus x plus h. Okay. And over here, I'll distribute the x, and I'll get x squared plus xh plus x over those same couple factors there. Okay, now how about we add those together, add the two fractions in the numerator of the big fraction, and here's what I will get. So it's going to be one big fraction in the numerator, the denominator will be that common denominator of x plus 1 over x plus h plus 1. I am not going to bother multiplying out the denominator right now, but I'll get x squared plus xh plus x minus h. And since I'm subtracting, remember I actually have to distribute this negative sign to all three of those terms up there. Right, we're taking the difference of those two polynomial numerators, and when we subtract polynomials, we have to distribute. So that's why I'm going to get minus x squared. Oh, sorry, this should have been plus h on the end there. Okay, looks good. Minus x squared minus xh minus x. And whole thing is over h still. This looks pretty good. X squareds cancel out, the xh's cancel out, and the x's cancel out. And I am just left with h over x plus 1 times x plus h plus 1. That is all in the numerator of the main fraction. We still have that h in the denominator of the big fraction. So now this is that kind of weird scenario where we have a fraction inside of a fraction, and how do we simplify this? Okay, the way that I think about this is there's a main fraction bar. Maybe I'll highlight it with blue. There's a main fraction bar there. And we can simplify. I'm noticing that we have this h in the numerator up here, and then we have this h in the denominator down here. The way that we can simplify this, there are a couple different ways to do it, but we could multiply top and bottom of the main fraction by 1 over h. So 1 over h, and multiply by 1 over h in the denominator. And what happens is we get cancellations with a bunch of these h's, right? That cancels with that, this cancels with this. So we just get 1 in the numerator up there, so we get 1 over x plus 1 times x plus h plus 1, right? And then in the denominator of the main fraction bar, we just get 1. So I'm not even going to bother writing it. So this is how it simplifies down. Okay, so that's a method you can use. People always get mixed up when we get into this situation where there's like a fraction inside of a fraction. This is a nice way to do it, where you just identify what is the main fraction bar, what is the big fraction bar, right? Looking back to the beginning of the problem, that's just that fraction bar that separates that original numerator from the denominator. And just multiply top and bottom by 1 over h, and that will deal with that for you. And we're left with this. So 1 over x plus 1 times x plus h plus 1. That is the simplified difference quotient for the function f of x, which is x over x plus 1. Okay, you might be wondering why we're doing this and why we care about this difference quotient. It's not just meaningless, superfluous math labor for you. It turns out that we're actually going to need this to define the derivative. So here we are. Let's talk about the derivative. Okay, so we're going to frame this as like an instantaneous rate of change, kind of like we were talking about in the earlier example. So first let's talk about finding the average rate of change of f as x varies from a to x. So looking at this graph down here, looking at the picture, a is a particular x value, and x is like, a variable. Okay, so this corresponds to the slope of the secant line, like we were talking about before. And we can calculate this slope of the secant line in the following way. So, I like to do the thing where I write out the ordered pairs, right? This ordered pair is a f of a, and this ordered pair is going to be x f of x. So the slope of that secant line is just going to be the difference of the y's over the difference of the x's. So that'll be f of x minus f of a over x minus a. Okay, and if we want to find the instantaneous rate of change at x equals a, it corresponds to the slope of the tangent line, like we already knew. And the instantaneous rate of change, m tan, is going to be the limit as x approaches a of f of x minus f of a over x minus a. So just the limit of this formula, which computes the slope of the secant line. And looking at the picture should make clear kind of why we set it up in this way. Remember, the slope of the tangent line can be found, like if we're looking to find this slope right here of this pink line, which is the tangent line. It's the line which only intersects the graph of f at that one point, P, or that's the ordered pair A, f of A. And we can compute that by looking at the slopes of the secant lines and taking the limit as x gets closer and closer to A, right? And we can sort of see the progression of these lines, right? As we let x approach A, as we take the limit, we see that the slopes of these secant lines are going to get closer and closer and closer to the slope of the tangent line, which is what we're after. Okay, so let's have a look at an example. For this one, for example 5, we're here on page 5. We want to find the equation of the line which is tangent to the graph of x squared plus x, that's this parabola here, at the ordered pair 1, 2. Okay, so down here looking at the picture, there's the graph f, that's a parabola, and we want to find the equation of this green line. Okay, so this green line here is the tangent line. At x equals 1, or at that ordered pair 1, 2. So we want to find the equation of that line. This type of example, we are going to see many of these. We're going to be doing these all semester long. Find the equation of the tangent line. This is a prompt you're going to hear many times throughout the semester. So let's jump into it using this definition that we just learned up here. Okay, so normally, at the beginning of one of these problems, just to orient myself, we want the equation of a line. What is the equation of a line? Well, remember, so y equals mx plus b, that's kind of the most common one. So I might just, to orient myself, think our answer will be in the form y equals mx plus b. And I write this just to, just to kind of make clear to myself what I'm really looking for here, right? I want the equation of a line. What do I need in order to determine the equation of this line? Well, there are two main values that we want to solve for. We want to find the slope, right? What is the slope? M. And then we want to find the y-intercept, b. Okay, so first we want to find the slope. Okay, so first we want to find m, which really in this case is going to be m tan, the slope of the tangent line. And based on this definition up here, it's going to be the limit as x approaches a of f of x minus f of a over x minus a. All right, so we got to figure out a couple things here. First of all, what is f of x? Well, that's just going to be this, x squared plus x. What is a? What are we going to substitute in for a? Well, looking back to the picture up here, the definition, remember a is just the x value, right? The sort of point on the x-axis at which, we're trying to solve for the tangent line. So in this case, a is just going to be 1. All right, so we want to evaluate this here where f of x is equal to x squared plus x, and a is equal to 1. Okay, so that's the first part of this problem, is just recognizing what we're trying to find, starting to find the slope of the tangent line, knowing we're going to have to use this formula here, and just establishing what is the function and what is the x value that we're looking at. Okay, so with that, we can now substitute in here. So really, I'm looking at the limit as x approaches 1, right? Because a is equal to 1. Of f of x minus f of a, so that'll be x squared minus x minus f of a, so a is equal to 1. So we just want to evaluate what is f of 1. So that'll be 1 squared plus 1. Sorry, this should have been a plus sign up here, x squared plus x. And then 1 squared plus 1. And in the denominator, we're just going to have x minus a is 1. Okay, so just to be extra clear right there, that is f of 1, right? So now we can simplify. So the limit as x approaches 1 of, okay, so 1 squared plus 1, that just gives us 0. Or, excuse me, it's going to give us 2. So we'll have x squared plus x plus 2 in the numerator, and then x minus 1 in the denominator. Okay, now we have to think back to chapter 2. We know how to evaluate limits. How do we evaluate a limit that looks like this? Well, can I direct substitute? No, I can't, because if I plug 1 into this function, I'm going to get a 0 in the denominator, so that is not going to fly. But remember, sometimes we can factor the numerator and denominator and get that sort of problematic factor that causes the 0 in the denominator to go away. So let's see if we can do that. If I factor the numerator, right, you could do a little diamond method. What two numbers multiply to 2 and add to 1? Sorry, this should be negative 2. Right, it was minus f of a. So what two numbers multiply to negative 2, add to positive 1? I think that 2 and negative 1. Right, so I can factor the numerator to x plus 2 times x minus 1, and the denominator is x minus 1. And would you look at that? Very convenient. That factor cancels out. So, sorry, kind of going off the page here. Limit as x approaches 1 of just x plus 2 is all that's left over. So we got lucky. We were able to simplify, and now we can evaluate the limit by direct substitution. This is just going to be equal to 1 plus 2, which equals 3. Okay, just a reminder, write limit as x approaches 1 for every single step until you finally evaluate it and actually substitute in that one. That's when you can finally stop writing limit as x approaches 1. Okay, and here's what we have found. So I'll write over here, so the slope of the tangent line is equal to 3. So I'll put a little, underline that. That's good, we're partway there. We found the slope. Now we just need to find the y-intercept. Okay, so I'll say now let's find b. All right, and there are a couple different ways to approach this. You can use the point slope form or point slope formula if you like that. You could do the solve for b method. I'll do the solve for b method this time. Remember, our answer is going to be in the form y equals mx plus b. And we just found that the slope m is equal to 3. And we can use the ordered pair, any point that's on this line, but we know that the point 1, 2 is on the line. So I'm going to use this ordered pair 1, 2. Right, and you might remember this from your intermediate algebra class. We can substitute in 1 for x, 2 for y, 3 for m, and then we're just left with that one variable b, which we can then solve for. Okay, so this is going to be 2 goes in for y. This is equal to m, which is 3 times x, which is 1, plus b. So see how I just substituted in those values that I have? And let's solve. So 2 is equal to 3 plus b. Subtract 3 from both sides. I get negative 1 is equal to b. Okay, so now I have those two things that I needed. I have the slope. I have that the y-intercept is equal to b. So I can finally give my answer. The equation of that tangent line is y equals 3x minus 1. Right, just plugging in 3 for m and negative 1 for b. So that's the equation to this green tangent line here. And looking at the graph, looking at the picture, we can sort of verify, or at least kind of do a sanity check. Like, does this seem like the right equation here? Yeah, I would say that it does. It looks like this y-intercept is going down here to negative 1, right? So it looks like it intersects the y-axis at 0, negative 1. And we have this point 1, 2, right? So to get to that point, we go up 1, 2, 3. We go over by 1 unit, right? So the rise is 3, the run is 1. So rise over run, it looks like the slope is equal to 3. Okay, so just kind of visually using the graph to check my work. If you're not given the graph, you could put it into your graphing calculator and approach it that way. Okay, but just going back to the beginning of the problem, just to remind ourselves like what we're asked here and just what the flow of this problem is to help you remember how it goes. If you're asked to find the equation of the tangent line and you're given a function and you're given an ordered pair, remember your answer is going to be in the form y equals mx plus b, and there's just kind of the two things you have to look for. Find the slope, and then you want to find the y-intercept after you have that slope. But start with the slope. And here we use this formula here. Okay, so I wish that it was as simple as just doing the difference of the y's over the difference of the x's, but remember, tangent lines, we only have one ordered pair, so we have to jump through this obstacle here and use the limit definition. Okay, so we use the limit. Our function was x squared plus x. The a value is 1. Plug that into the limit. Simplify and then try to evaluate the limit. So you'll have to lean on the skills we developed back in chapter 2. But if you do everything correctly, you should end up with just some real number. In this case, it was 3. Right? And then from this point forward, really it's just an intermediate algebra problem. Right? No calculus to be done here. We're just going to solve for that y-intercept. And that'll give us our answer, which will be in the form y equals mx plus b. Okay, so that's one way of defining this like slope of a tangent line or instantaneous rate of change. given a function f and some particular x value a, there's another definition, which actually is going to be the one we use more frequently. Let's have a look at this definition. We will look at x going from a to a plus h. As the 2 points get closer together, h will get closer to 0. Okay, so this should feel a lot more similar to that example we were doing with the Mars, the rock being thrown upwards on Mars. The width of this interval here is h. Okay, so rather than looking at the limit as x goes to a, like we did in the last example, we can look at the limit as h goes to 0. It's totally equivalent to what we were doing before, but just set up a little bit differently, and the math ends up working out a little bit better, I think. So, okay, what's the average rate of change? So the slope of the secant line between these 2 points, it'll be the difference of the y's, which is going to be f of a plus h minus f of a, over the difference of the x's. That'll just be the width of that interval there, which is going to be h. Okay, and then the instantaneous rate of change is going to be the limit as h approaches 0 of that expression up above, f of a plus h minus f of a, all over h. Okay, so this is another formula for the slope of the tangent line, and one that's going to be more useful in many cases. Or more common, I should say. So for example 6, pretty much same type of question as example 5. We want to find the equation of the line tangent to the graph of, here we have a cubic function, x cubed minus 3x plus 1. And we're looking at this ordered pair 2, 3. Okay, so we are not given the graph of this one, so we're just going to rely on the process here. So I usually start these problems by thinking, okay, my answer is going to be in the form y equals mx plus b. So I want to find m, I want to find b. I usually start by finding m. So let's find m, which is going to be the slope of the tangent line. And we have a formula for that. We're going to use this new one, the limit as h goes to 0 of f of a plus h minus f of a all over h. And we want to evaluate this when f of x is x cubed minus 3x plus 1. And what is a for this problem? Correct. It's going to be just the x coordinate of the point where we are trying to find this tangent line. So a is going to be equal to 2 in this case. So now we substitute all that stuff in. So we're going to look at the limit as h goes to 0 of, and you see a long fraction bar like that, it's going to be a little rough, but it's okay, we'll get through it. F of a plus h. So we got to do that thing where we substitute a plus h into the function. Here's what it'll look like. It'll look like a plus h cubed minus 3 times a plus h plus 1. Okay, and maybe I'll put grouping symbols around this. Blue grouping symbols to indicate what is coming from where. Okay, and then the next term, we're going to do minus f of a, and that's just going to be a plugged in. Oh, here, I'll tell you what. I'm gonna do this in a couple steps here. We can just write f of a, which is a cubed minus 3 times a plus 1 all over h. So that was kind of dealing with the function part. But remember, a, we actually have a particular value for a. A is equal to 2. So let me substitute 2 in for a now. So it's going to be 2 plus h squared minus 3 times 2 plus h plus 1 minus, and then, okay, 2 cubed minus 3 times 2 plus 1. And I'm going to look over my work real quickly to make sure I didn't make any mistakes. It's very, very easy to do. One thing to point out here is keep grouping symbols around this second thing, around f of a, because we're subtracting. So remember, we're going to have to, distribute that negative sign. But I'm actually going to simplify inside of the parentheses, but make sure you put those grouping symbols there. It'll mess up the arithmetic if you don't. Okay, so it's going to get a little worse before it gets better here. So if we multiply out 2 plus h, sorry, that should be cubed. 2 plus h cubed, I might do this off to the side. That's 2 plus h times 2 plus h times 2 plus h. So you can FOIL this out, or do it however you like to do it. Multiplying out 2 plus h times 2 plus h, you get 4 plus 4h plus h squared, and then we want to multiply this by 2 plus h. You can then take this and distribute it in. That's how I see a lot of people doing it. Okay, so you can do all that, but I'm going to skip ahead a couple steps just to save time on the video. Here's what I get after simplifying. So multiplying that out there, I have to distribute this -3 into here, and then I got to add with the 1. When all the dust settles, you should be left with 3 plus 9h plus 6h squared plus h cubed. Okay, and then minus, this simplifies down to 3, right? That's the 2 cubed minus 3 times 2 plus 1. This is all still over h. Okay, so the most grueling part, the most challenging part of any of these problems where you're trying to find the equation of the tangent line is just doing this limit work, simplifying it and evaluating the limit. That's the hard part. But we're getting real close here. The numerator simplifies. We have +3 and we have -3, so those will zero out. And I'll have the limit as h approaches 0 of just 9h plus 6h squared plus h cubed all over h. All right, so I'm just working on simplifying this as much as I can. And what I'm hoping to see is this h in the denominator cancel out, because remember, I'm trying to take the limit as h goes to 0. And for as long as there's an h in the denominator, I can't direct substitute, right? Because I'll get a 0 in the denominator, that's a no-go. So the hope is always that problematic factor that makes the denominator go to 0 when we do the direct substitution. We're hoping that goes away. And I think we're going to get lucky here, because look, we have a common factor of h in the numerator. So I can pull out an h, and I'm left with 9 plus 6h plus h squared. This is all over h. That's a common factor of h. Cancel those out. And I am just left with the limit as h approaches 0 of 9 plus 6h plus h squared. And I can finally just direct substitute in that 0, and this whole thing goes to 9. And God, what was this again? What were we trying to find? What is 9? That's the slope. That's the slope of the tangent line. So that's great. I'm relieved that part is over. Now that I have the slope is 9, right? M tan is equal to 9. So now I just have to find b. So, okay, y equals mx plus b. I have that m is equal to 9. I can substitute in for x and y. Let's use the ordered pair that we were given, 2, 3. Okay, so then I use the ordered pair 2, 3, which I know is on the line because this is the tangent line at that point. So it has to contain that ordered pair 2, 3. So let's plug in 3 for y, 9 for m, 2 for x, and we can solve for b. So 3 equals 18 plus b, subtract 18 from both sides, and I get that b is equal to negative 15. So my answer is going to be y equals 9x minus 15. Okay, so we can totally check our work using a graphing calculator. So I think I'm going to go show you how we would do that real quick. So let's have a look at our calculator and how we might check this work. So here we are looking at our graphing calculator. If you hit the y equals button, this is where you can type in your functions. And here I have our original function, x cubed minus 3x plus 1. And then our answer that we got for the equation of the line tangent to this function at the point 2, 3. Okay, so I typed that in. Hitting the Windows button, this just is where we can decide which portion of the coordinate plane we want to see. I just have our window going from negative 10 to 10 on both the x-axis and the y-axis. Okay, and I'm going to go ahead and hit graph, and let's see what happens here. So remember, what we want to see is we want to see these two lines intersecting at the specific point 2, 3. So I'm going to hit graph. Let's see what we get. Okay, so that first curve was the cubic function. That second line was our tangent line that we just found. It looks like it's intersecting at the desired point. We can zoom in a little bit to get a better look. So if you hit the zoom button and hit zoom in, which is number 2, you could go down 2, or you could hit the number 2. And I'm going to move this cursor. You can see that little point moving. I'm just going to move it over to the general area where we see these curves intersecting, and you could hit enter. That should give you a little better view. Okay. An even better way to verify for sure that it intersects at that point is using the intersect function. So if you hit second and then the trace button, which is going to bring up the calc menu, you'll see this. We can scroll down to intersect, or you could just hit the number 5. Okay. And now what it's going to say is first curve, and see how it's highlighting the cubic function. We're going to hit enter, and then it'll say second curve, and then we see the linear function is displayed up there. So we'll hit enter. That's just specifying those are the two functions that we want to be observing and trying to find the intersection point. Guess just means put the cursor close to the intersection point that you want to identify. So that looks good to me. I'll hit enter and see what it says. It's thinking. So it says that the intersection is at 1.9999996, 2.9999996. Okay, this is basically just saying the point 2, 3. Your calculator might just say 2, 3. Mine is a little older, so maybe that's why mine does this. But ultimately, the way calculators work is they're not like finding equations of tangent lines. They have a different kind of iterative process that they use that sometimes results in a funny thing like this. But this means that we were correct. It intersects at the point 2, 3, so this verifies our answer that we found in that last problem. Now that we verified this answer here, we can move on. And here we are, we finally made it to the derivative. So in those last examples, we computed the slope of a tangent line at one fixed point for one given function. If the point is moved, the tangent line moves and generally the slope changes. So this is kind of an issue because like for this last problem, okay, we just did all that work of finding the equation of this tangent line. What if then I said, okay, you know what, rather than looking at x equals 2, actually I want to know what's happening at x equals -1. Right? If we then wanted to look at a different x value, we basically have to do this whole problem over again, even though the only thing that changed was the a value. Okay, so the derivative, what it's going to do is it's going to sort of generalize this process so that we can quickly, find a new type of function that will help us get the tangent line of, any type of function at any given x value, assuming the function is differentiable at that point. Okay, so let's define the derivative. The derivative of a function f of x with respect to x is the function f prime of x. That's the notation we use. And it is given by this formula. The derivative f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. The process of computing the derivative is called differentiation. And we say that f of x is differentiable at x equals a if the derivative f prime of x exists at a. Okay, some might say f prime of x is defined at a. I choose to say exists at a because the derivative is a limit, right? And for this derivative to be defined, really it means that this limit exists. Okay, so notice that this formula is nearly identical to this formula that we're looking at up here. The only difference is instead of using a, some particular input or some particular x value a, we are just generalizing it and we're just leaving that as a variable x. All right, that's really the only difference here. So let's do an example and kind of explore what the derivative is, how we find it, and how we use it. So we want to find the derivative for this function x squared plus x. All right, well, we have our formula up there. So we want the derivative f prime of x. And this is going to be equal to the limit as as h approaches 0 of, and then the formula is f of x plus h minus f of x all over h. Sorry, that kind of looks like a plus sign. Minus. And now what we want to do is we want to substitute in the function f of x into this formula. So here's what that will look like. This is very similar to what we did on that previous example, but we just don't have an a value. So f of x plus h, that just means take x plus h and plug it into the function. So that'll look like this, x plus h squared plus x plus h. And I'm going to group that together. Minus f of x. And that's just going to be x squared plus x. The grouping symbols are really important, mainly because this is subtraction here, so we have to remember to distribute that negative sign when we simplify the numerator. That's really easy to forget, so that's why I'm always really careful to put those brackets in there. So now we want to simplify this, so let's do that. I'll have to multiply out x plus h squared to begin with. That'll give me x squared plus 2xh plus h squared, right? Because we have to FOIL, plus x plus h, and then minus x squared minus x, distributing that negative sign like I mentioned. This simplifies a bit. The x squareds make a 0, the x and the x make a 0. The limit as h approaches 0, now we're looking at just 2xh plus h squared plus h all over h. All right, and I'm pretty happy with what I'm seeing here because, remember, we want to take the limit, we want to let h go to 0. From the beginning of the problem, there's an h in the denominator. So we can't do direct substitution in the first step, and sorry for the bad news, but we're never going to be able to when we're taking a derivative, right? Because it's just worked into the formula that we have an h in the denominator. So there's always going to be some process of simplification and hoping that that h in the denominator gets canceled out. Like really, we're hoping to find a factor of h in the numerator. And that's why I say I'm happy with what I see here, because I see that there's a common factor of h in the numerator. So limit as h goes to 0 of, I'll factor out an h, and on the inside I have 2x plus h plus 1 all over h. And hooray, the h's cancel out. So we've got the limit as h approaches 0 of 2x plus h plus 1. And finally, I can actually evaluate the limit. I can let h go to 0. That's just going to make this term drop out, and I'll just be left with 2x plus 1. Okay, remember to carry along this as h approaches the limit part. Like you have to write that every time until you actually let h go to 0, then you can finally drop it. So here's what we found. I'll write our answer over here. So f prime of x, the derivative, is equal to 2x plus 1. So this is interesting. Our answer is a function, right? The derivative is a function. It's not just a real number. So what this derivative does for us is it's essentially a machine which spits out the slopes of tangent lines given an input value x. Okay? So this function that we started with, x squared plus x, this is the same function we were working with in example 5. And remember, we went through all this work and we found that the equation of the tangent line at the point 1, 2, so associated with the x value 1, we got that the slope was 3, and this was the equation of the line right here. Okay, so let's go back to the problem at hand. So working with the same function. And let's say that I want to look at, that point that we saw in example 5. Let's look at x equals 1. So here, I'm going to do a little demonstration here, or a little example. So let's say that we wanted to find the tangent line at the point 1, 2. Okay, we already did this, so we know what it's going to be. We know we're going to have a slope of 3. But let's check that. Let's find that using the derivative. So what the derivative does is it tells us that the slope of the tangent line should be equal to the derivative evaluated at a. So plug in 1 into this function. Okay, I get 2 times 1 plus 1, and I get 3. Okay, this is exactly what we were expecting. This is what we found in example 5. So, and then you could go through the work of finding the y-intercept like we already did, but you'll find the tangent line looks like that. The equation of this tangent line was y equals 3x minus 1. Okay, let's say that, actually I want to find the equation of the tangent line at x equals -2. So another little example here. How about let's find the tangent line at x equals -2 this time. Okay, well, the slope of the tangent line at that point should just be equal to the derivative f prime evaluated at -2. So I'll plug that in, 2 times -2 plus 1. This is going to give me -4 plus 1. I'll get -3. Okay, so at -2, looking at the graph, that's this point right here. The slope here, according to the derivative, is going to be -3. Okay, and this intuitively, it makes sense because, given the symmetry of the parabola, notice that this point right here is like totally aligned with that other point, the ordered pair 1, 2. So I would expect this slope to be the same, but just opposite, right? Going in the negative direction. Okay, and the derivative just gave that to us really, really quickly, right? And then of course you could go through the work of finding the y-intercept. That would take just a second. Maybe just doing one more. This point down here at the vertex. So what do we think the slope of the tangent line should be down there at the vertex? That looks like a horizontal line. So I would guess that the slope is equal to 0. Let's see if the derivative verifies that, right? So let's find at x equals -0.5. So let's find f prime of -0.5 or -1/2. That'll be 2 times -1/2 plus 1. And we can simplify this. It becomes -1 plus 1. We get 0. All right, so the derivative allows us to, just generate this function which spits out the slopes of the equations of tangent lines. It turns out that this is one of the most useful mathematical discoveries of all time. Okay, people who are going to study engineering or really anywhere where there is change, right? So any of the sciences, business, this is incredibly helpful, social sciences, and so on. Wherever there is change relative to time, the derivative is helpful because it gives us the slopes of tangent lines, which gives us the rates of change of functions. More about that later. Let's just try another one of these. We're still just getting used to the math and the machinery of generating these derivative functions. Next, we want to do f of x equals 1 over x. So let's do it. We want to find this derivative. So the derivative f prime of x is just going to be the limit as h approaches 0 of, what's the formula again? F of x plus h minus f of x. I'm really good at memorizing formulas because I write them down every time that I use them. If you haven't learned that about me already. Now I'm going to just substitute in my function. So this is going to be 1 over x plus h minus 1 over x all over h. Let's try to simplify this, right? Because I can't direct substitute. No surprises there. I have this weird fraction and a fraction thing going on. I usually try to simplify and get out of that situation. So how about we add these two fractions in the numerator together by getting common denominators? I'll multiply this function top and bottom by x. I'll multiply top and bottom of this one by x plus h. Okay, so I'm going to pursue this. I don't know if this is going to work, but we just got to try something and go for the low-hanging fruit. This just seems like the most kind of natural way to proceed. So let's do it and see if we get what we want. So this will be x over x times x plus h minus, in this numerator we'll have x plus h over x times x plus h, and the denominator of the main fraction is still h. I put grouping symbols around this x plus h here because remember we're subtracting, so I have to distribute that negative sign to those two when I subtract these two fractions now that we have common denominators. So here's what we'll get. We'll get x minus h, right? Distributing the negative sign all over x times x plus h. Big denominator is still h. All right, so the x minus x is going to go to 0. So now I'll just have negative h over x times x plus h, all divided by h. All right, so now I think that we can get out of this fraction and a fraction issue. The way I usually do this is, we have this main fraction bar here. The two most common ways is you can multiply top and bottom by 1 over h. That will help cancel out that h down there. Another way that people do, which you're totally welcome to do it this way, is turning the main fraction bar into a division sign. So just to demonstrate another way to do this. So negative h over x times x plus h. If you turn that main fraction bar into a division sign, so we're just dividing by h. To divide by h is the same as to multiply by the reciprocal 1 over h. So this is the same as times 1 over h. And then we get this h up here to cancel with that h down there. They make a big 1. So then this is equal to the limit as h goes to 0 of just negative 1 over x times x plus h. And this is where I find out if my approach here was effective. Can I let h go to 0 without getting a 0 on the denominator or anything weird like that? Yes, I can. I can let h go to 0, and this just becomes negative 1 over x times x plus 0. So just x times x in the denominator. So negative 1 over x squared. So my derivative, I'll write my answer up here. F prime of x is equal to negative 1 over x squared. So now if we wanted to find an equation of a line which is tangent to this curve f of x equals 1 over x at any x value in its domain, we can just plug right into this derivative function and it will spit it out for us. Okay, let's do another one. The square root function. I'm kind of covering some of the most important, most common types of functions, polynomials. This is the parent function for a rational function, 1 over x. Square root function is another really important, like toolkit function, we sometimes call them. So let's find the derivative for this one. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, fine, I won't write out the formula this time. Let's just put in to the square root. That's what we get when we substitute in the square root function. Now, how might we simplify this? We've seen examples in the past where we had, taking limits of functions involving square roots and fractions, because we're hoping to do something here to manipulate this algebraically in such a way that that h in the denominator goes away. So the approach that we used in the past was multiplying by the conjugate. So multiplying by the conjugate, that is taking that expression in the numerator, changing the sign of one of the terms. So really this is a technique we use when we have a sum or difference involving a square root or a radical. So what I'm going to multiply top and bottom by is the square root of x plus h plus the square root of x. So just changing the sign of that root x. And okay, so this gets a little bit ugly. It gets worse before it gets better. Because, okay, we're multiplying these together. And in the numerator, we're technically multiplying two binomials together, right? Like if we were multiplying x plus y times x minus y, how do we multiply this out? Well, we'd have to, FOIL it out, or box method, however you like to deal with it. So that's what I'm going to do here. So multiplying the first together, that's going to be root x plus h times root x plus h. Okay, or I could just write that as root x plus h squared. Okay, kind of taking the FOIL approach first and then outer, so that'll be root x times root x plus h. Inner, that's going to be negative root x times root x plus h. And last, that's going to be negative root x times positive root x, so negative root x squared. And this is all over h times root x plus h plus root x. I'm not going to multiply out the denominator because remember, I'm trying to get that h to cancel out. So I'm going to leave that as a, in factored form so that if I get a factor of h in the numerator, I'll be able to cancel out with that one and I should be able to evaluate the limit. So some nice stuff happens here. I have positive positive root x times root x plus h and negative root x times root x plus h. So those make a 0. Square root squared, those will cancel out. Right, because x squared and square root of x are inverses of each other. Of course, just assuming that x plus h is positive, or x is positive, since it's in a square root. But that's not a problem because remember, our original function was the square root of x. So it might be worth noting, note x is going to be greater than or equal to 0. Okay, so here I'm just left with x plus h, and then minus x. That's all we're left with after all that dust settles. All right, and then we have a positive x and a negative x, and I'll just be left with positive h in the numerator. I am really happy to see that. I just have h up top. In the bottom, I have h times the square root of x plus h plus root x. The h's make a big 1. So now I'm just looking at the limit as h goes to 0 of 1 over root x plus h plus root x. My hand is getting tired. And I think I could finally let h go to 0, so I'm just left with 1 over the square root of x plus 0 plus the square root of x, or this simplifies to 1 over 2 root x. So that can just be our answer. So the derivative f prime of x is equal to 1 over 2 root x. And I'll put a box around that. Okay, so it's a good thing we got all that practice in chapter 2, finding, evaluating limits, because the derivative, which is a huge topic and a massively important one in calculus, requires that we can evaluate limits of all different types. So a nice reminder of this little, multiply by the conjugate rule. Okay, next example. We're going to talk about graphs of derivatives, because derivatives are functions, right? Like this derivative that we just found is a function. We could graph this derivative function. You can make a t-table, plug in x values, get out y values, and you can totally graph this function on the xy coordinate plane. So for example 10, this one's kind of interesting. We're given the graph of this function f, and we want to come up with the graph of f prime. We're not told like what the expression is for this function. We're just given the graph of it. But since we know that the equation, or the slopes of the tangent lines of the original function, are going to be the output values of the derivative function, we can figure this out by looking at this graph. And it works with this type of graph that we see here because it's really apparent what the slopes of the tangent lines are. So if I just picked a point on the graph, like, okay, how about this one over here? This is at x equals -4. What does it look like the slope of the tangent line is at this point? So remember, the tangent line just perfectly mimics the slope of the graph at that point. What does it look like the slope of the graph is at that point, or at that ordered pair -4, -2? What does it look like this slope is? Well, it looks like it goes up 1 over 1, right? So the slope of the tangent line, right? Like if we want to know what the slope of the tangent line is, that'll give us f prime of -4. We could think of this as being rise over run. Rise over run. The rise is 1, the run is 1. It looks like the slope is just equal to 1. All right, so if we were trying to generate the graph of f prime, like we are over here, you could even do a t-table, right? The input values and the output values. If we put in -4 into this derivative function, it looks like we're getting out 1. Okay, so I'm just going to sort of build this up using a t-table. Let's plug in another value, like let's say that we're looking at, how about x equals -2 this time? What does it look like the slope of the tangent line is at -2? Well, it's the same as at -4. It looks like the slope is still +1, right? So if I plug in -2 into the derivative function, it looks like I get out +1 again. Same with -1. Same with 0. Same with 1/2. All the way up until we get to x equals 1. Okay, let's talk about x equals 1 in just a second. On the other side of x equals 1, like if we're looking at, what's the derivative equal to at +2? Well, what's the slope of the tangent line at +2? It looks like f prime of +2, again taking the rise over run approach. Here it looks like, okay, the run is 1 unit, the rise is -1 unit. So it looks like the slope here is -1. Okay, so if I plug in 2, -1 is the slope. Same with 3. Same with 4. Right, and it appears for the rest, up to infinity. All right, so far here's what my graph of my derivative looks like. To the left of x equals 1, we are just outputting +1. And to the right of x equals 1, we are just outputting -1. So now the question, what is happening at x equals 1? So let's look at that point at x equals 1. What's happening? Well, to the left, to the immediate left of x equals 1, the derivative is equal to +1. To the immediate right of x equals 1, the slope is -1. What does that mean for the derivative at x equals 1? Well, if we go back to the definition of the derivative up here, this is what defines the derivative. The limit as h approaches 0 of all this stuff, essentially the slope formula. So notice that this is not the limit as h approaches 0 from the left or from the right. This is just the limit as x approaches 0. So the two-sided limit, right? The derivative is defined as a limit, a two-sided limit. So what we have here is it looks like the left limit is equal to +1 and the right limit is equal to -1. What do we say when the left and right limit do not equal one another? We say that the limit does not exist. Okay, so at x equals 1, so here I'm going to highlight this one in red. At x equals 1, the derivative, since it's defined by a limit, the derivative does not exist. So this is undefined. Or maybe you'll say does not exist. So at x equals 1, we're not going to have a filled-in bubble. I'm just going to do 2 open bubbles indicating that the derivative is not defined at that point. So what we call that point there is a sharp point. Okay, derivatives cannot be defined at sharp points because of this, left and right limit problem. So this is it. Here's the graph of our derivative function. It's just, these two branches. One is a horizontal line at y equals 1 up to x equals 1, and then to the right of x equals 1, we just have a horizontal line y equals -1. Okay, so more on this about like, okay, derivatives, sometimes they're not defined, obviously. You know, that's what we learned in this last example. What are the particular scenarios where the derivative is not defined? That's what we're talking about here. So if any one of these holds, f is not differentiable at a. Okay, so if f is not, the first one, if f is not continuous, at a, it will not be differentiable there. Okay, so like looking at this first picture here, at this point, that is a discontinuity, right? I cannot draw the curve across x equals -1 without picking up my pen. So it's not continuous, therefore it's not differentiable. The second case, if f has a sharp point, that's what we were just talking about. If f has a sharp point at a, it's not differentiable, so that's like what's happening in this picture at x equals 2. Again, left and right limit, which calculates the slopes of the tangent lines. It's not going to agree, so it's not going to be defined at that point. And the last one is if f has a vertical tangent line. So like looking at this second picture right here, at x equals 0, what does it look like the tangent line is? It's this vertical line here. What is the slope of a vertical line? Well, remember, slope is rise over run. A vertical line has a run of 0, so the rise might be some number, but the run is going to be 0. And this is undefined, right? We can't divide by 0. Okay, so if we have a vertical tangent line, that can only mean that f prime of a, you know, wherever that vertical tangent line occurs, is undefined. All right, so those are the three cases to watch out for: discontinuous functions, sharp points, and vertical tangent lines. That's where the function will not be differentiable. And that brings us to the end of 3.1, which is a heavy section. This is a big, heavy section. It's a lot of work, but I have some really, really great news for everyone. It turns out that finding derivatives in many, many cases is much, much easier than what we were doing in these examples back here. The derivative comes, you know, the origin of it is from this limit definition, but it turns out there are a lot of techniques which allow us to evaluate and compute derivatives much more easily and much more quickly. Okay, so section 3.2, you're going to get some really great relief from a lot of that work that we did. In section 3.1, techniques of differentiation. So I will see you there in the next video.